All right, buckle up, everybody, because today we are diving deep into the world of photons.
Oh yeah, get ready for a brain twister.
We'll be exploring an essay called Photonen, Grundbaustein der Quantentechnologie by Jörg O. Schneeppert.
It's all about photons and why they are so important in quantum technology.
So before we get lost in the quantum weeds, let's just start with the basics.
Sure.
What exactly are photons, and why should we care about them? I mean, we all know what light is, right?
Well, we experience light every single day, but it's a lot more complicated than it seems.
Okay.
You see, photons are like these tiny little particles of light. They are the building blocks of light, and they are the key to all sorts of amazing technologies, like lasers, the things we use to play music and even perform surgery with.
Right, right.
And get this, they are even crucial to building quantum computers, the computers of the future.
Whoa, so they're not just like tiny little light bulbs zipping around then.
No, not quite. One of the most mind-boggling things about photons is that they actually behave as both a wave and a particle.
Wait, what? Hold on. How can something be two things at once?
I know, it's crazy, right? It's called the wave-particle duality of light. So there's this famous experiment called the double-slit experiment.
Yeah.
You shine a beam of light through two tiny slits, and what you see on the screen behind it is an interference pattern, just like what you'd expect if light were a wave.
Okay, that makes sense.
But here's the kicker. If you slow down the light enough, you can actually see individual photons hitting the screen.
So it's like they're acting like tiny bullets.
Exactly. It's as if light just can't decide whether it wants to be a wave or a particle.
That's wild. So if photons are these particles of light, does that mean their energy changes depending on the kind of light we're talking about? Like, is the light from the sun different from, say, the light from my phone?
You got it. The energy of a photon is directly tied to its frequency. So higher frequency light, like ultraviolet light from the sun, has more energetic photons, and that's why it can give you a sunburn.
Makes sense.
Lower frequency light, like the infrared light coming from your TV remote, has lower energy photons.
Okay, so the frequency of the light determines how much energy each photon has.
Exactly. Now, the essay also mentions something called Planck's constant.
Yeah, to be honest, that part kind of went over my head.
Yeah, it's a bit of a head scratcher.
What's the deal with Planck's constant?
Okay, so Planck's constant is this fundamental constant in physics.
Okay.
And it basically defines the smallest possible amount of energy that can exist. It's like, imagine the universe as a giant computer screen, and energy is like the pixels that make up the image.
Okay, I'm with you.
Now, you can't have less than one pixel, right?
Right.
Well, it's the same with energy. You can't have less than one photon's worth.
Oh, okay. That's a good analogy.
It was revolutionary because it showed that energy isn't this continuous thing. It comes in these tiny little packets, these quanta.
So, like, it's quantized.
Exactly.
Okay, so photons have different energy levels, and there's a limit to how small those energy levels can get because of Planck's constant.
Right.
But Schneeppert, he also talks about this stuff called polarization and spin.
Yeah.
What's that about?
Imagine you're throwing a frisbee.
Okay.
As it flies through the air, it's spinning, right?
Yeah.
And it has this specific orientation. Well, just like that spinning frisbee, a photon has this property we call polarization. It describes how the photon is oriented as it travels.
So it's like the photon is pointing in a certain direction.
You got it. And it can point in one of two ways, which we call spin.
So it's like spin up or spin down.
Exactly.
Okay, I'm starting to see how these photon properties could be useful. Is that where things like quantum communication come in?
You're catching on quick. You see, all these unique properties make photons incredibly powerful for things like secure communication. For example, in quantum cryptography, we can actually use the polarization of photons to create encryption keys that are virtually unbreakable.
Unbreakable, huh? That sounds like something straight out of a spy movie. How does that even work?
Well, Schneeppert describes this protocol called BB84. It basically uses the fact that any attempt to measure a photon's polarization will actually change it.
Really?
Yeah. So if someone tried to eavesdrop on a conversation, one that's using these photon keys, we would know immediately because the key would be altered.
That's incredible. But the essay also mentions this other mind-blowing concept, quantum entanglement.
Right, that's a fun one.
What's that all about?
Entanglement. It's one of the weirdest things in all of quantum mechanics. It's where you get these two photons that are linked together no matter how far apart they are.
What do you mean linked?
It means that when you measure the state of one entangled photon, you instantly know the state of the other one.
Even if they're miles apart?
Yep. even if they're on opposite sides of the galaxy.
Wait, so you're saying you could change one photon and the other one would change instantly no matter how far away it is?
Precisely. It's as if they can communicate faster than the speed of light, which, according to Einstein, should be impossible.
Yeah.
But here's the thing. It's a real measurable phenomenon. It's mind-blowing.
My head is officially spinning. We've got these photons that can be used for unbreakable codes and seemingly instantaneous communication.
It's pretty wild, isn't it?
But how do they actually fit into this whole quantum computer thing?
That's where things get even more interesting.
Okay.
In a normal computer, the kind we use every day, information is stored in these things called bits.
Right.
And a bit is either a 0 or a 1.
Go.
But photons, thanks to their quantum properties, can act as qubits.
Okay, so what's the difference between a bit and a qubit?
Well, think of it this way. A bit is like a light switch. It's either on or off, right?
Right.
But a quid, thanks to this principle of superposition, it can be a little bit on, a little bit off, or both at the same time.
So qubits can be in multiple states at once.
Exactly.
That's incredible.
And it's precisely this ability that gives quantum computers the potential to solve problems that are impossible for regular computers.
I can see why people are so excited about quantum computing.
Yeah.
But Schneppet mentions there are some challenges with actually using photons for quantum computing.
Right.
What are some of the hurdles they need to overcome?
Well, one of the main challenges is building a quantum computer with a large number of qubits.
Okay.
You see, photons are also prone to loss and decoherence, which basically means they can lose their quantum properties over time. And that can make computations unreliable.
Yeah, that makes sense.
It's a delicate balancing act trying to build these systems.
It sounds really complicated.
It is, but researchers are working on some really ingenious solutions like quantum error correction codes.
Oh!
Yeah, and they're also exploring different approaches to building these computers.
Okay, so what are some of these different approaches? I'm curious.
One really promising approach is called linear optical quantum computing, or LOQC for short.
LOQC.
Yeah, and it's all about manipulating photons using, basic optical components, things like mirrors and beam splitters.
So it's like they're building a quantum computer with lasers and mirrors.
In a simplified sense, yeah. Schneppet mentions this theoretical framework called the KLM protocol. And it basically shows that, in principle, a universal quantum computer could be built using just these simple optical elements.
That's amazing. But are there any other ways to build these computers?
Oh, definitely. Researchers are also looking into using these things called integrated photonic chips, which are basically they're like tiny little chips that combine a whole bunch of optical components onto a single chip. This approach could make the system more compact, more stable, and maybe even easier to manufacture.
Okay, so LOQC uses mirrors and lasers, and integrated photonic chips are like miniaturized versions of that.
That's a good way to think about it. And of course, there's a lot of research being done on improving the actual sources and detectors for the photons, because those are critical for making the whole thing work.
Makes sense.
It's a rapidly developing field.
It sounds like there's a lot of creativity and ingenuity going into building these photon-based quantum computers.
Oh, absolutely. There's so much potential there.
So what kind of problems could these computers solve if we manage to build them?
Well, Schneppet highlights some really interesting applications, things like drug discovery and material science. You see, quantum computers could be used to simulate the behavior of molecules at the atomic level.
Oh, wow.
This means we could design new drugs and materials with incredible precision.
So we could, design new materials on a computer instead of having to do years of experiments in a lab?
Exactly. And that's just the tip of the iceberg. Quantum computers could revolutionize fields like finance, cryptography, and artificial intelligence.
Oh.
We're talking about unlocking possibilities we can't even imagine yet.
It sounds like we're on the verge of a real technological revolution.
It's an exciting time to be alive, that's for sure. But before we dive into all that, Schneppet also talks about using photons for something called quantum sensing and measurement.
All right.
Now, that's a whole other can of worms, but it's equally fascinating.
Quantum sensing, what exactly is that?
So it's all about harnessing the incredible sensitivity of quantum systems to measure things with extreme accuracy. And you guessed it, photons are perfect for this.
Okay, but can you give me an example?
Yeah.
How can you use these tiny little particles of light to actually measure things? I'm having trouble picturing it.
Sure. Think about LEGO, the observatory that detects gravitational waves, those ripples in space-time caused by massive objects colliding.
You mean like black holes colliding?
Exactly. And you know what LEGO uses to measure these incredibly subtle distortions? Lasers. And lasers are essentially just focused beams of photons.
Wow, that's already pretty impressive.
Oh, it goes even further. Researchers are building atomic clocks that are so precise they can measure the differences in Earth's gravitational field over just a few centimeters.
Really? That's insane.
It is. And these clocks could have huge implications for everything from GPS to fundamental physics research.
That level of precision is mind-boggling. What else can these quantum sensors do?
Schneppet also talks about some exciting developments in quantum imaging, which uses entangled photons to create images with much, much greater resolution than traditional microscopy.
So you mean like we could have crystal clear images of cells and molecules instead of blurry ones?
Exactly. And that's not all. These sensors could detect tiny changes in magnetic fields, temperature, and even the presence of specific molecules.
Okay, so the applications are pretty broad.
They are. We're talking about advanced navigation technologies, new diagnostic tools, environmental monitoring systems. The list goes on and on.
Wow, it seems like photons really are the unsung heroes of the quantum revolution. They're not only driving advancements in communication and computation, but also pushing the boundaries of what we can measure and observe about the world around us.
Couldn't have said it better myself. But I'm curious, what do you think about the current state of research in this area? What are the key areas of focus right now?
That's a great question. There's been so much progress, but it seems like there are still some big challenges ahead.
Oh, definitely. What do you think are the biggest ones?
Well, developing more efficient and reliable photon sources seems crucial.
Right. And why do you think creating these sources is so difficult?
It seems like it all comes down to control and precision.
You're on the right track.
We need to be able to generate single photons or maybe even pairs of entangled photons on demand and with very specific properties.
Exactly.
But current methods for generating single photons are often inefficient, which limits their practicality.
Yeah, it's kind of like trying to control a fire hose to release a single drop of water.
Huh. A good analogy.
But don't worry, there are some breakthroughs happening. Schneppet talks about using quantum dots, which are these tiny little semiconductor nanocrystals, and they can emit photons with very specific wavelengths and properties. So they're showing a lot of promise as efficient single photon sources.
That's good news. What other research areas are particularly active right now?
Well, another critical area is improving photon detectors.
Okay.
We need detectors that are super sensitive, can operate at room temperature, and can differentiate between different types of photons based on things like polarization or wavelength.
So it's like we need a high-speed camera with night vision and color recognition, but for photons.
You got it. And these advanced detectors are really important for everything from quantum cryptography to quantum imaging.
I see.
It's incredible how much work is being done in this field.
It really is. So from your perspective as an expert, what do you think are some of the biggest unanswered questions or challenges that still remain?
You know, one of the biggest challenges for me is understanding the fundamental limits of what we can do with photonics. Like, how much information can we actually pack into a single photon? How far can we transmit entangled photons before they lose their connection?
Yeah, those are some deep questions.
They are. We're really just beginning to explore the full potential of photons, and I think the most exciting discoveries are yet to come.
Absolutely. And the more we learn about photons, the more we realize just how much potential they have for shaping the future of technology and, well, maybe even the future of humanity itself.
I couldn't agree more. It's an incredibly exciting field to be a part of.
Well said. It's been a mind-bending journey so far, exploring the world of photons with you.
Likewise.
And it seems like we've only just scratched the surface of this fascinating topic.
Oh yeah, we've got a lot more ground to cover.
But for now, let's take a quick break.
Sounds good.
We'll be back soon to delve even deeper into the incredible possibilities of photons and their potential to revolutionize everything from communication and computation to our understanding of the universe itself.
Stay tuned. You know, Schneppet paints this really fascinating picture of what the future could look like, with photons playing a starring role.
Oh, yeah.
Yeah. He sees them as this key to tackling some of humanity's biggest challenges, like healthcare and even climate change.
Whoa, hold on. Tackling climate change with photons? How does that even work?
Well, he talks about developing these super efficient solar cells using those quantum dots we talked about earlier.
Right.
They could capture way more of the sun's energy than traditional solar cells.
So we could, power our homes and cities more efficiently.
Exactly. Imagine a world running on clean, abundant solar energy.
That would be incredible.
It would. And that's not all. He also talks about using photonic sensors to, monitor the environment with incredible accuracy. We could track pollution levels, greenhouse gas emissions, even detect early warning signs of natural disasters.
All thanks to photons.
Precisely.
That's wild. But with all this talk about these advanced technologies, are there any ethical concerns we should be thinking about?
That's a great point, and Schneepat definitely acknowledges those concerns.
I mean, any powerful tool can be misused, right?
Exactly. And he specifically mentions how quantum computers could potentially break our current encryption methods.
Oh, no.
Yeah, it could pose a serious threat to cybersecurity.
That's kind of scary.
It is, and that's why Schneepat stresses the need to develop quantum-resistant cryptography alongside these other advancements.
So it's like we're in this technological arms race, always trying to stay one step ahead of the bad guys.
That's a good way to put it. We need to make sure our data and communications stay secure, even in a post-quantum world.
Okay, so security is a big concern, but are there any other ethical dilemmas Schneepat brings up?
He also touches on the potential impact of these quantum technologies on jobs.
Oh, right.
Like any new technology that automates things, there's a risk of job displacement.
Yeah, it's like the classic robots taking our jobs scenario.
It's something we need to address proactively, for sure. Schneepat suggests things like investing in education and retraining programs to help people adapt to a more quantum-driven economy.
That makes sense. We don't want to leave anyone behind in this technological revolution.
Exactly. Everyone should have the opportunity to benefit from these advances.
Okay, so security and jobs are big concerns, but I'm curious, what are some of the frontiers Schneepat seems most excited about? What's on the horizon for photonics?
Well, he's really enthusiastic about the development of a true quantum internet.
Wait, didn't we already talk about that with quantum communication?
We touched on it, but a full-fledged quantum internet would be a whole other ballgame.
Okay.
Think about it. A network that can transmit quantum information, like entanglement, across vast distances.
That sounds incredibly complex.
It is, but it would also be incredibly powerful. We could create this whole new paradigm of distributed quantum computing.
So instead of just having one super powerful quantum computer, we could have a whole network of them working together.
Exactly. And Schneepat believes this could lead to some major breakthroughs in fields like medicine, material science, and even fundamental physics.
That's amazing.
Yeah.
But before we get too carried away with the future, let's circle back to something you mentioned earlier. Ethical considerations.
Right.
I think it's really important to remember that technology is just a tool.
It is.
And ultimately, its impact depends on how we choose to use it.
Well said. We have this responsibility to make sure these powerful technologies are used for good.
Absolutely.
And that their benefits are shared by all.
We need to proceed with both excitement and caution.
I agree.
It's a delicate balance.
As we explore the quantum realm, we always need to consider the potential consequences of our actions.
Right, because the future isn't predetermined, it's something we actively shape.
Exactly. It's up to us to guide these technologies in a direction that benefits all of humanity.
Well said. We've covered so much ground today, from those bizarre quantum properties of photons to their incredible potential to revolutionize technology and tackle some of our biggest challenges.
It's been quite a journey. And we owe a lot of these insights to Jorgo Schneepat and his thought-provoking essay.
Absolutely. His work has given us a lot to think about, that's for sure.
And while we've touched on a lot, I feel like we've only scratched the surface of this rapidly evolving field.
Me too. But for now, let's take a moment to reflect on everything we've learned.
Okay.
And as we move forward, let's remember to approach these powerful technologies with a sense of responsibility and a commitment to using them for the betterment of humanity and our planet. You know, it's incredible when you think about it.
Yeah.
Photons are everywhere.
They are.
From the tiniest cells to the vastness of space.
Yeah.
It's remarkable. So as we wrap up our deep dive into Jorgo Schneepat's essay, is there like a final takeaway, a big picture idea that he leaves us with?
I think what really struck me was his optimism. He really believes that photonics can solve some of humanity's greatest challenges.
Oh.
He envisions a future where we have all this clean energy thanks to advances in things like solar power,
Yeah.
advanced healthcare, with new imaging techniques and therapies, and even a deeper understanding of the universe.
All because of photons.
It's pretty amazing, isn't it?
It is. It's like this tiny little particle of light.
Yeah.
It could hold the key to all these incredible advancements.
Exactly. Of course, there's still challenges to overcome, right?
Of course.
But I think Schneppat's work is a really powerful reminder that we need to keep researching and exploring in this field.
Yeah.
Because the more we learn about photons, the more possibilities we unlock.
That's a good point.
And who knows, maybe we're just scratching the surface of what's possible with this incredible technology.
It's been a mind-blowing journey, that's for sure.
It has. I feel like I've learned so much.
Me too.
And you know what?
Yeah.
I think this is just the beginning. There's so much more to discover, so many more questions to answer.
Exactly. And who knows, maybe some of the people listening to this deep dive, they'll be the ones to make those groundbreaking discoveries.
That would be awesome.
It would. So to everyone listening, stay curious.
Yes, stay curious.
Keep asking questions.
Yeah.
Because the future is bright, and it's powered by photons.
Couldn't have said it better myself.
A huge thank you to Jorgo Schneppat for his fascinating essay that sparked this conversation.
Absolutely.
And thanks to all of you for joining us on this deep dive into the amazing world of photons.
It's been a pleasure.
We'll see you next time.